Hello everyone, welcome to Control System course. In this video, I am going to discuss how to determine the transfer function from the given block diagram. So to determine the transfer function from the given block diagram, we can apply block diagram reduction techniques. First of all, I will explain that technique. Later, I will explain how to find out the transfer function from the block diagram using signal flow graph. So first of all, go through the block diagram reduction rules. So based on the given block diagram reduction rules, always we have to identify the series combination, cascading combinations. If any cascading blocks are connected, first of all simplify that. So if the blocks are connected in cascading or in series, then the total transfer function is product of the individual gains. And later we have to go for parallel combination. If the number of blocks are more than the one blocks are connected in parallel, then the total transfer function is algebraic summation of individual gains. And third step we require the closed loop. If the system has any closed loop path or any closed loop blocks, then write the transfer function. Just replace that complete closed loop by the single block. That block gain is a g of s by 1 plus j of s into h of s. So we have to follow the standard closed loop transfer function formula. After completion of these three steps, we have to go for the fourth step. The fourth step explains shift all summing points towards the left side of the block diagram and shift takeoff point, all takeoff points towards the right side of the block diagram. Then the simplification becomes easy. So that purpose we have to follow this technique. So always try to shift a summing point towards the left side of the block and shift a takeoff point towards the right side of the blocks. So now go through the given block diagram. This block diagram has a G1 of s, G2 of s, G3 of s, G4 of s, G5 of s, H1 of s and H2 of s. These are the individual transfer functions. So totally it has these transfer functions, individual blocks and connected in series and parallel. Some combinations are there. So first of all, try to identify the first step. First step explain the series combinations. Now go through this one. G1, G2 are not connected in series. G2 and G3 also not connected in series because here one takeoff point is defined here. This point is called takeoff point. That's why G1 and G3 not connected in series, and similarly G3 and G4 also not connected in series because one more takeoff point is defined here. And later parallel connection is not possible and the loop connection is also not possible directly. First of all, here we have to apply shifting of takeoff points based on the given diagram. Summing point shifting is not required. Just I want to shift this takeoff point. All of you observe this diagram. This takeoff point to this position. Otherwise, you can shift this takeoff point towards the left side or this takeoff point towards the right side of the block. So just I want to shift this takeoff point towards the right side of the block. Based on the given diagram, this takeoff point is shifted. This takeoff point is shifted to this position. So I am drawing the takeoff point from here onwards. Here onwards, it is connected to the one block. So whenever the takeoff point shifts towards the right side of the block or after the block, this block gain divides within that path. So already G5 of s is the transfer function of this path, and this block gain, whatever the block gain, because the takeoff point is shifted towards the right side of this block gain divides within this path. So G3 of s is divides here. Then finally, which gives the one simple block like this, G5 of s by G3 of s. Now the simplification becomes very easy here because now these two are connected in series. I will write that one now. G2 of s, G3 of s, these two are connected in series, and again this G4 of s, this block, these blocks are connected in parallel. So first of all, we have to simplify the series blocks and parallel blocks. So if the blocks are connected in series, then the total transfer function is product of the individual transfer functions. So G2 of s and G3 of s is there. Write the product of these two. And similarly, these two blocks are connected in parallel. Then this is also replaced by one single block. Then what is the transfer function of this one? Algebraic summation of these two. One transfer function is G4 of s plus this transfer function is G5 of s by G3 of s. So replace these two blocks and draw the remaining diagram as this. So the remaining diagram I wrote as this now. So these two are simplified and these two blocks also simplified. Now go through the any other steps. Series combination finished, and parallel combination also finished, then go through the closed loop. So within this here, one closed loop function is defined, this path here. Just I'm drawing the dotted line. This is acts as a one closed loop system. So apply here closed loop transfer function formula. This explains the forward path gain and this explains the feedback path gain. So then the transfer function formula explains a forward path gain by 1 minus r plus here. Minus is given, so you have to write the plus. So negative feedback purpose, you have to write plus. So 1 plus a forward path gain into feedback path gain. Just I want to replace this complete block. Feedback path gain is h1 of s, so multiply here. This gives the standard transfer function of closed loop system. So finally, I have replaced this closed loop path, and the remaining diagram is as this. Draw the as this here remaining part. So try to simplify this one here. G4 into G3 plus G5. The remaining blocks I'm drawing as this. So finally, here I have applied this complete loop is simplified here. Then these three blocks are comes under series, and this complete function acts as a forward path, and feedback path is h2 of s. Finally, I want to write the final transfer function formula. Forward path gain, product of all this 1 plus this complete function into h2 of s. This is a standard transfer function. Later we can cancel this G3 here, G3 get cancels, G3 get cancels, and later take the LCM, then try to write the final transfer function formula. Just here I explained how to find out the transfer function from the given block diagram using block diagram reduction technique, right? So this technique takes a more number of steps, because here every time we have to redraw the circuit, and it's a time consuming part also, and it takes more time to solve or to determine the transfer function from the block diagram using block diagram reduction rules. That purpose, here I want to explain one simple technique of how to write the transfer function of the given block diagram using signal flow graph. First of all, I will explain how to draw the signal flow graph of the block diagram. So in signal flow graph, node and lines are used. That node is acts as a summing node and takeoff node. Block diagram representation consists summing point, takeoff point, and the transfer function of the block. But signal flow graph consists only node and lines. In this case, summing point is counted into. So to convert the block diagram to signal flow graph, we have to replace the summing point as a node, and similarly takeoff point as a node. Takeoff point also acts as a node, and summing point also acts as a node, and this whatever the block, that block acts as a aroma representation. Just you have to drive the gain of that block only. So for easy understanding purpose, first of all, identify the summing points and takeoff points. See, here one takeoff point is there, just I'm giving the number for this, takeoff point 1, and this is summing point, so summing point 1, and later it has one more takeoff point. Just try to identify the takeoff points and summing points. So here it has one more takeoff point here, so already T1 I wrote here, so just I'm writing here, this is T2, and one more summing point is defined here, this is S2. Give the names for that, and later summing point here defined, this is S3, and here one more takeoff point, this one is a T3. So from the given block diagram, identify the takeoff points and summing points and give the names for those summing and takeoff points. And later we have to assume all summing points and takeoff points are as a nodes. So that purpose, first of all, I'm drawing one input node. Every diagram requires compulsory one input node, and later follow the order. After the input node, it has takeoff point 1. Let us take T1 here, and summing point 1. Just try to write as a nodes. Okay, takeoff points as a node and summing point also node. So again, takeoff point is there. So here I'm writing a T2. Write the names also. Summing point S2 and summing point S3, and here takeoff point T3, and finally we have to write the output of the system C of S. So write, convert and replace each takeoff point. Replace each takeoff point as a node and each summing point as a node, and similarly assume one node is an input node, one node is an output node. Then go through the diagram. So input to the takeoff point node, up to takeoff point node, there is no transfer function. That's why draw one line with a 1 gain, right? The gain of that one is 1. And takeoff point 1 to summing point 1. Here it has direct one path. So T1 to S1 direct one path is there. Then write the gain of this one is 1 because there is no gain within that path. First of all, draw the complete forward path. Summing point 1 to takeoff point 2. It has one block gain. Just observe these two here. S1 to T2. So S1 to T2 it has block gain. So draw one arrow mark like this. What is the gain here? G1. So G1 of S, right? G1 of S. Similarly, takeoff point 2 to T2 S2. T2 S2, one more gain is defined. So T2 S2, one more gain, that is G2. Again, S2 to S3. S2 to S3, another block is defined. The gain of that one is G3. Write one arrow mark and write the gain of that. And similarly, S3 to T3. There is no blocks from that. In between S3 and T3, write the gain is 1. If the blocks are not defined, write the gain is 1 here. T3 to C of S. Here our gain is not there. Write 1. Then go through the combinations. See, T1 to one forward path is defined here. T1 to directly S3. One complete path. One path is defined from T1 to S3 with the gain G4. Then draw one line T1 to S3. So draw one line like this directly. T1 to S3 and write the arrow mark here and write the gain of this one is G4. Similarly, find out the remaining paths here. From T2 to S1. Here one path is defined. T2 to S1. So T2 to S1. The direction is from T2 to S1. So feedback direction is there. So write arrow mark like this. And what is the gain of this one? H1 of S. But here it is adds by the minus sign symbol. That's why we have to write minus H1. Similarly, one more path is defined here. T3 to S2. So T3 to S2. Draw like this. And the gain of this one is H2. Minus symbol is there. So then write minus H2. So finally, I have replaced the complete block diagram by the signal flow graph. So draw the signal flow graph, then find the transfer function from the signal flow graph, apply the Masson's gain formula, find out the number of forward paths, and find out the individual loops, and find out the 2 non-touching loop pairs, 3 non-touching loop pairs, then substitute all this into one standard Masson's gain formula there, which gives the transfer function directly. So compared to the block diagram reduction techniques, signal flow graph takes very less number of steps and it takes very less time to find the transfer function. So that's why always try to use this technique. So block diagram to signal flow graph, later find the transfer function from the signal flow graph.